All right. So today, again, we're starting a new section. There's a bunch of reactions in here. Um, so we're going to start up top with the reactions of alcohols, and this is a quadrant. Yeah, well, the worksheet is in quadrants, so each set of reactions is kind of building on the previous set. So that first set of reactions, we're going to really talk about alcohol, um, using alcohols as reagents to make esters, and also um, to make ethers. Right. Then the second quadrant down here is oxidation of alcohol, so turning them into carbonyls. And then the third quadrant is converting alcohols into alkenes, as well as converting alcohols into acetals and hemiacetals. And then hopefully you watched the video I sent yesterday as well. What was it yesterday? Monday. Um, and then also amides, were reactions of amines, and using those to make amides, amines, as well as amines, right? Or synthesis of amines, which is that bottom reaction. There's a bunch of problems on here. I'm gonna have to pick and choose which ones we actually do, because we just don't have time to do everything on here, but I'll worry about that part. And yeah, so what I want to do first is I'm gonna just cut this out, introduce that first section, get my stylus. And yesterday Monday when I sent the announcement, I told you where to find this. It is in the in-class submission, in-class handout submission folder and the assignments folder, or the assignments content area on Blackboard. So hopefully you grabbed it. It's going to be kind of hard to follow this, trying to write it all down. So it's best to get the handout. But I'm going to put this on a blank sheet so we can start with this first set of reactions. All right. So with the first set of reactions, we're going to talk about our reactions of alcohol, right? And then we're going to talk about these three simple reactions. And let me say this too, because I always try to stress this. The key to understanding like what's happening with these reactions, well, there are actually two keys. One is knowing your functional groups, and I can't stress that enough. I don't, if you at this point in your organic matriculation and don't know your functional groups, you're in trouble when it's time to take a standardized exam for med school or for dental school or pharmacy school or whatever. You're in deep water. So you need to know your functional groups, and you also need to know some basically differences with nucleophiles and electrophiles, right? Or acids and bases. Really, they follow the same, very similar principles. But you got to know those things in order to know what's going to attack what, which pair of electrons is going to move, all that type of stuff. But all of that is considered a part of that, what we call working knowledge from part one, which was in the syllabus on the first day of class when we talked about like what it's going to take to get through the class and be successful. So the first reaction is what we call a transesterification. So this is just a simple ester synthesis. And both of these are, but they just do it different ways. Right. So one of the things about carbonyls is when you react them, we talked about this when we did granular addition to carbonyls. One of the things about carbonyls is that when you react them, they don't do substitution, they do addition. And then sometimes they'll do elimination to get back to the carbonyl and reestablish that bond. So both of these reactions, the transesterification and the esterification, wrong pen, work on the same principle. So I'm gonna start with the top one. And the bottom one, we'll work through that one too, right? But the top reaction, you need a carboxylic acid and an alcohol, and you need a little bit of dilute acid as a catalyst. And you have to do this under thermal conditions. So you got to heat it up. And if we look at the reaction itself, I just want to go through the mechanism for that. And then we're going to go through the mechanism for the second one as well. So here's my alcohol. Put some electrons in, plus the acid. And I'll just leave that as an R group, right? In this reaction, that catalyst, that is going to be some dilute acid, right? So what you end up doing first, excuse me, is protonating, right? Doing proton transfer with the carbonyl, and that will activate the carbonyl to react faster. That's why it's called a catalyst. So now you got this intermediate, right? So now that's activated, right? It's ready to react. The dipole is a little bit stronger towards oxygen now, and the carbonyl carbon is more susceptible to nucleophilic attack. So that's where your alcohol comes in. So you have your alcohol here. That's just going to attack that carbonyl like so, right? This is all chemistry that we've seen before. Nucleophiles and electrophiles, acids and bases, nothing new. So now you'll have another intermediate. This is now OH. Anybody remember what the name for this intermediate would be when you attack a carbonyl and you get an intermediate with 4 substituents on it? Anybody remember the name of that? Right, it's a tetrahedral intermediate. Probably, but some days it's like talking to a brick wall. All right, so the tetrahedral intermediate is one intermediate. And then now we need to, I don't think it's up here. Well, it is up here. We need to lose water. How will we do that? We got 2 OH groups, and let me put a charge on oxygen right here. We got 2 OH groups, and we need to turn one of them into water. Let's think about turning this bottom one into water. How would you do that if you wanted to make that into water? What's the best proton source to find a proton to give to that hydroxyl group? Anybody?
Hi, I just joined. I'm a little confused as to what's going on. I'm sorry. What was the question?
The question was, I want to make one of those hydroxyl groups into water. What can I do? What is there a proton that's readily available to give to this hydroxyl group to make it into water? Because I need to get water to leave.
Could you take that cation and push some arrows?
You mean like this? So
Yeah.
I can take that proton, and then those arrow, that pair of electrons will end up on oxygen. And so now I'm going to have another intermediate. This reaction has a lot of intermediates. And then this is going to be water. All right. And then now I need to get rid of water. So anytime you do an addition with as your initial reaction, which is what this step is right here, right? In order to reestablish that pi bond, you have to do an elimination. So we're going to do that here. So this can eliminate like this here, boom, and then you lose water. So this is going to give me this. That's still positive. And my oxygen is going to be here. So I'm almost home, right? This is close to an ester, but it's not quite the same. So I need to get rid of that proton. So I need to do another proton transfer with that same water that just left. Right, so I'm just going to pick that proton up like so, give these back to oxygen, and then that'll get me to my ester, which is here. And I've regenerated the acid. Right, so all these reactions, and if you watch the video that was sent out on Monday, or if you previewed that part of the chapter, this is not foreign. It shouldn't be foreign to you. It should at least be a little bit familiar. So that's the mechanism for transit esterification. With the other reaction, I don't need a catalyst with the acid chloride reaction. Right, acid chlorides are highly reactive. So I'm reacting that with the same alcohol, right? And it's going through all the initial steps are identical, right? So just like the transit esterification, I'm going to attack the carbonyl, right, with the oxygen from the alcohol, because that's my nucleophile, and I'm going to end up with a tetrahedral intermediate that looks like this. And then this is where my alcohol attack. Right, this is a much faster mechanism. Actually, those acid chlorides react with anything. When you open the cap to the bottle, they start reacting with the water in the air. Like it's that fast. Right, so this is the addition step. And then, of course, I want to get to the ester, so I'm just going to eliminate like so. All of your carbonyl reactions are going to be additions followed by some type of elimination, unless the tetrahedral intermediate stays as it is, like if it gets trapped or something like that. And you can do that. You'll see that when we do the acetal and hemiacetal formation. Right, so once that elimination happens, you have your ester. And again, both of these methods work fine. It just depends on what you're trying to do. Transit esterification works well. Using the acid chloride also works well. It just depends on your preferred method. And it depends on what type of ester you're trying to make. Because if you have a bulkier alcohol, then it's better to probably use that acid chloride method because it's much faster, much more facile. All right. Questions about that, about those two reactions? All right, let's go to the last reaction, which is an ether synthesis, Williamson ether synthesis. Again, if you have trouble with your functional groups, then if I say ether and you have no idea what that is, then it's not going to mean anything to you. But ether is this functional group right here. We have oxygen with a bond to carbon, a single bond to carbon, and that R is a generic, carbon containing group. Right? It can be anything, but it has a single bond to carbon on either side. Right, and the way this works, it's very simple. This works via SN2 type substitution, which we already studied. And the base that's here simply does a proton transfer with the alcohol first to make it a better nucleophile. Right, everything goes back to the basics: nucleophiles and electrophiles, acids and bases, everything. There's nothing that we will study. I don't care how advanced you get in chemistry. There's nothing you can study that doesn't go back to the basic principles of, especially when you're talking about doing reactions. There's nothing that won't go back to those basic principles of what's a nucleophile and what's an electrophile. Now there's some more advanced ideas around that, but at the core is basic organic 1, right? Everything in organic 2 just builds on what we did in organic 1. So when I react this with sodium hydroxide, right, the hydroxide is just going to act as a base and then just pull that proton off right there. Like that. And then the OH bond breaks. So you end up with, let me make sure. So now this is your nucleophile. When I take that and react it with the alkyl halide, that can be any alkyl halide. I'm just going to do methyl chloride, right? When I react that with that alkyl halide, it's just a simple SN2 type substitution. Right, so the water came from here. That OH pulling off of the proton to give you water. And then once that chlorine gets released, the sodium from NaOH ends up with that chlorine, right? But this is, ether synthesis is simply SN2 substitution on an alcohol. That's it. But these initial reactions are, and I did this on purpose, these are very simple mechanisms to think about because this stuff we've already seen. We've seen Grignards attack carbonyls and how you get tetrahedral intermediates and then how they can eliminate or how they can stay put, right? We've seen that already. So that's why this shouldn't be completely foreign to you. All right, let's go to any questions about that? Right, let's go to the next quadrant then. The next, we're not going to go through these mechanisms because they're a little bit more complicated than time will allow. But the SWERN, all of them are readily available. If you want to go to what is it, organic chemistry portal, you can type in SWERN oxidation and it'll pop right up and give you the mechanism. But the SWERN oxidation is a way to oxidize primary alcohol. So if you notice, you have methods for primary and secondary, but no tertiary, right? And there's a reason for that. Tertiary alcohols cannot be oxidized. Right, there's a reason for that. When an alcohol gets oxidized up to a carbonyl, right, you have to have something, it has to be possible for that alcohol to do what's called hydrogen shuttling, right? So you need to be able to remove both of these hydrogens, the OH proton as well as the carbonyl proton. Right, you got to be able to take both of them off. And so in doing so, right, you, in effect, you lose H2, right? But at the same time, you have created a carbon oxygen pi bond. Right. So that's why if you have a tertiary alcohol, you cannot oxidize it because there is no carbonyl proton, right? This is the hydroxyl proton here. And then this is what we call the carbonyl proton. If you have a tertiary alcohol, you don't have that. Right, because a tertiary alcohol would be this, right? So you have the OH proton, but no carbonyl proton. Right, so because of that, you can't oxidize it. That's a lot of information about this process, but it's necessary. So when you look at alcohol oxidations, all you're looking at is either primary or secondary alcohols. And there are specific methods, just like when we did conversion of alcohols into alcohol halides. You have specific methods for different types of alcohols, for primary, for secondary, and with that process for tertiary. But here, you have methods that are specific to different types of alcohols, right? So this is primary. And so there are two methods you can use for that. There are a lot more, but we're just gonna focus on these two. So you can do Swern oxidation, or you can do chromic acid. Oxidation. Both of those work just fine, right? Both of those will take a primary alcohol. And if you look at the product, the primary alcohol is going to get, again, functional groups, very important, is going to get converted into an aldehyde, right? This is the aldehyde functional group right here. There's a hydrogen on that carbonyl, right? So if you do Swern or chromic acid, it's going to give you an aldehyde because on a primary alcohol. If you take a secondary alcohol, look at the difference. I don't know why this thing is freezing up, right? This is TPAP and NMO. TPAP is an acronym for tetrapropyl ammonium perruthenate. It's a ruthenium catalyst. It's a ruthenium catalyst. And a lot of these alcohol oxidations are catalyzed by transition metals. like you see, like with chromic acid and TPAP, both the ruthenium and chromium are both transition metals. But if you look at the alcohol itself, it's secondary, and then the product is a ketone, not an aldehyde. Notice the difference here, you got a carbonyl, and on either side of that carbonyl, you have a carbon. Right, for the aldehyde, you got a carbon on one side, hydrogen on the other side. Right, so the TPAP NMO oxidation is going to take that alcohol and convert it into a carbonyl. Right, so what we'll do today, I'm just going to walk through it, and then on Friday, we're going to go through some of those reaction wheels and start predicting products, because for this section, we're not going to do mechanisms for the oxidation part. All right, questions about either one of those? Right, if you look over here in this box, primary alcohols get oxidized up to aldehydes, secondaries get oxidized to ketones, and then tertiaries do not oxidize. Right, and when we think about oxidation in general chemistry, when you learned about oxidation, what did that mean to you when you were taking Dr. Biswas or Dr. Gines or Dr. Curry or Dr. Trene or Dr. Reeves? What did it mean when something got oxidized? Anybody?
To remove the oxygen.
Say again.
Remove the oxygen.
If something got oxidized, and when I'm talking about in terms of general chemistry, it had to do with the number of electrons, right? It either gained electrons or lost electrons. So when something got oxidized, it lost electrons. When something got reduced, it gained electrons. Well, when you're thinking about oxidation in terms of organic chemistry, it's either you're increasing the number of bonds to oxygen or you're decreasing the number of bonds to oxygen. So all of these processes increase the number of bonds to oxygen. That's oxidation. And then decreasing the number of bonds to oxygen is reduction. So let me write that somewhere. Right here. So when something is oxidized, that means you increase the number of bonds to oxygen. Right?
Did you
Increase the
put
number.
this handout? I'm sorry.
Say again.
I said, did you put this handout on Blackboard by any chance?
It's there. I put it in the announcement on Monday where to find it. I think it was Monday when I sent that out. Yeah. It's in the assignments tab, assignments content area, and it's the last in-class handout submission. It's called final reactions worksheet or something like that.
It's not there for me.
Hold up. What I can do is just download it and then put it in the chat. To get on Chrome, which is not opening right now. Come on, computer. I think for Christmas, I'm gonna buy myself a new computer. This one it's a bucket. Let's see. Any questions about the oxidation, alcohol oxidation? Let me see. was able to download this document, but it's quite possible that that link is hidden. Yeah. Yeah. Let me upload this to the chat because the link was hidden. Sorry about that. Son of a biscuit. All right. Let me upload this right quick. And then if you're on a device, you're not going to see it. But if you're on a laptop, you'll be able to see it. All right. It's there in the chat. All right. Any questions about alcohol oxidation? Any questions about ester synthesis before we move to another quadrant? We got a few minutes left, so I wanna definitely do the Vidic reaction, and then we'll probably stop there and pick it up on Friday. All right, let me cut this out because I need some room to work with this. And I think it's important to understand, like when we're looking at these reactions, very important to understand, like these are not just, this ain't just some random stuff that's kind of pulled out of space, right? You have to actually understand that these are reactions that are used like every day to do some transformation, to make some new compound or some new drug or some whatever. So that's why we study them, because they actually have wide use, right? So this reaction is what we call the Vidic. I know it's W, but it's pronounced like a V. It's a German word. And the Vidic is used to take aldehydes and ketones and convert them into alkenes. This means nothing unless you understand the functional groups. What is an aldehyde? What is a ketone? What is an alkene? Like those things matter, because if you see it and you don't know what it is, then you're not gonna know how to approach the problem. So yeah, so if you look at the reagents, this is the dead giveaway that tells you that it's a Vidic. It's triphenylphosphine. That's the dead giveaway that when you see that, you know it's a Vidic reaction. And if you know it's a Vidic, then you know that the carbonyl is going to get converted into an alkene. I'm gonna show you a shortcut method for how to predict the products here. Because if you notice, this is my carbonyl is here. And then on the other side, on the product side, it's an alkene, right? And we're going to talk about how it works before we end the discussion, but I want to show you a shortcut method, because there are three key things that you need to do this reaction, aside from the carbonyl. You need an alkyl halide, and again, you're going to see some SN2 chemistry. You need an alkyl halide, you need a base. This is potassium butoxide. We've seen this before when we did elimination reactions. potassium tert butoxide. The tert is for that tertiary group right there. All right, and so you need a base, alkyl halide, and trophenylphosphine. A shortcut to thinking about this is to look at whatever that alkyl halide is. Right, so the alkyl halide is CH3Br. Right, if you notice the carbon, I have it in pink on purpose, that pink carbon, that's what replaced the oxygen, right, in the carbonyl. So oxygen was here, and then that pink carbon from the alkyl halide is what replaces oxygen in the product, right? So the way a shortcut method to thinking about this is, for if this is my alkyl halide, I'm going to, when I say subtract out, you can't literally do this, but I'm just using this as an analogy. I'm going to subtract out HBr, right? So I'm going to take away one hydrogen and the bromine. What would I be left with if I did that?
CH2.
CH2, good. Right, whatever I'm left with, that's what I'm going to replace oxygen with. So if this is my carbonyl, then this is going to be my alkene. Right, that's a shortcut way of thinking about it. If you don't know the mechanism, you can at least predict the products, right, which is very important. So if you take out one hydrogen and the halogen, because it's not always going to be bromine, it can be iodine, it can be chlorine. But if you remove HX, whatever you're left with, that's what's going to replace oxygen. And it's also important to understand that if I have a different alkyl halide, something like this, right, it's this carbon in the alkyl halide right here that ends up replacing oxygen, right? It's that carbon. It's always the carbon bonded to the halogen and the alkyl halide that ends up with oxygen, right? So let's go through that mechanism. It's a fairly involved mechanism, but we can knock it out. We can do it. All right, so the mechanism, I'll box that in, is kind of multiple steps. The first step is right here. I have in this box that it occurs via what we call an illet. And that's just this species right here, where you have a positive and a negative charge right next door to one another. And that illet can also be represented like this, right? Where you have a carbon and you have a double bond between carbon and phosphorus. You can write it that way because of resonance. So you can, if you see the illet in either form, it's still an illet. If there's a carbon with a double bond to phosphorus, or a carbon and phosphorus single bond with both atoms charged, it's still the same thing. All right, so the first step is to make that illet. I love doing Wittig reactions as a grad student, to be just being real, because it gave you a lot of time in between steps. So the first step is to prepare the illet. This is a step where you set up and go to lunch. All right, and normally it's done at low temperature. So in order to do that, let me just write this out. So I have CH3 Br, and then triphenylphosphine. So this is SN2 chemistry. I'm going to substitute the bromine with phosphorus. So this is going to attack here, and I'm going to lose bromine. Even though it doesn't want to attack from that side, it'll be a backside attack because it's SN2. I'm just putting the arrows in. All right, so once I do that, I'm going to get to this. That's now positive, and then this is CH3 plus Br minus, which is going to hang out over here and make a salt. All right, so that's not the end of it though, because I need that carbon to be negative. And so that's when I use my strong base. So the first step is SN2 attack. Of triphenylphosphine. And let me go back to, because when we talked about aromatics, I don't remember if I mentioned that, but pH is an abbreviation for a benzene ring. So this is phosphorus with 3 benzene rings attached to it. All right, so that's that. And then I need to do proton transfer with my base. So the base is going to come in here. And it's going to just pull off this proton. All right, so then that's how I get my illage. So that's going to be negative now. This is positive. And it's this illet is what attacks your carbonyl, right? And with that, when it does attack, there's well, I'm not going to say a debate. There was one accepted mechanism prior to some further research that showed that you don't get this intermediate that everybody thought existed. But I'm gonna do that on Friday. I don't want to do that now. Plus, it's in the video that I sent too. So make sure you watch that. So you'll come Friday ready for battle. But there's an accepted mechanism, or a previously accepted mechanism, and a previously accepted intermediate that no longer is accepted because there was some work done that kind of disproved that the existence of that intermediate. And we'll talk about that on Friday. So I'm gonna stop here. Any questions? All right, if no questions, we will pick up Friday. If you have questions between now and then, feel free to ask them, email, text, however.